All right, so for question number 3, a couple things to remember. First off, position versus time graph. Okay, things I can get off a position time graph, position and time. Okay, I can calculate displacement because I can see all the positions. I can calculate distance because I can see all the positions. And I can calculate velocity because that's position divided by time. Okay, so those are the things that I can get off of this graph. All right, so if I'm looking at this graph, the first part wants to know what's the displacement from 0 to 4 seconds. All right, so we got to remember that displacement is final position minus initial position. Okay, so we've got final position minus initial position. Our final position is -4 meters, okay, and our initial position is 0. Okay, so our total displacement during that would be -4 meters, right, or 4 meters backwards. Okay, questions on A? Okay, for part B, the total distance traveled over the whole trip. All right, well, we already figured out this part. It's 4 meters. How far does it go here? Nowhere. Okay, and then from here it goes from -4 to +6, so that's another 10 meters. Okay, so the total distance should be 14 meters. All right, everyone follow what I did there? Average speed over the whole trip. Well, I just figured out the total distance. I'll need that, okay, because speed is total distance over total time. Okay, the total time is 6 seconds. All right, so we'll have 14 over 6, okay, which should give us 2.3 meters per second. And then lastly, average velocity over the whole trip. All right, so I haven't calculated the total displacement over the whole trip yet, and I'm going to need that. All right, so that's going to be final position minus initial position divided by time. So my final position is +6, my initial position is 0, and the total time is 6 seconds. So we're looking at +1 meter per second as our average velocity over the whole trip. Okay, making sense? All right, how many people are working on 4 right now? How many people are done 4? Okay, good. Let's just have a look at it then. So we have a velocity versus time graph here, okay? What's happening between 0 and 2 seconds here? Nothing. It's actually stopped, okay? Because its velocity is 0. Okay, and then what's happening here between 2 seconds and 5 seconds? It's accelerating negatively, okay? And then between 5 seconds and 7 seconds, it's accelerating positively. What about here? It's traveling at a constant speed. That's the one we got to watch, right? Yes, here the flat line meant it wasn't doing anything because the velocity was 0. But up here, the velocity is 2 meters per second. So constant velocity 2 meters per second, okay? A negative acceleration, then a positive, then a constant velocity, then a positive, then a constant, then stopped for the last second. All right. Okay, so we want to calculate the acceleration between 12 seconds and 14 seconds. All right, so the acceleration, and we talked about this the other day as well, is VF minus VI over T, or the slope of any section of the line. All right, so we've got final velocity at 14 seconds is -6, okay, minus our initial velocity, which is +2. And then we're dividing that by 2 seconds because that's how long there is between 12 and 14 seconds. All right, so we have -8 over 2, which will be -4 meters per second squared, okay, which is meters per second per second. All right, questions on A? Okay, for part B, total displacement over the whole trip. Is this calculation a pain in the neck? Yes. Okay, it's a pain in the neck because we've got to do all those area calculations we looked at the other day, right? We want to take average velocity, okay, and multiply it by time in order to get distance or to get displacement. But the problem is that the velocity is constantly changing in this graph. All right, so I have to isolate different sections of the graph and calculate the displacement in each of the sections and then add them all together at the end. All right, so obviously the displacement rate here is 0. Same with right here. So I don't have to worry about those 2 sections because there's no displacement there, right? But I do have this triangle right here, okay, where I have, you know, it's going down to -3, okay, and we're looking at that happening over 1, 2, 3, 4 seconds, okay? So we'll have our, well, actually, we should probably do it this way. We can look at it as 2 separate triangles or one, doesn't really matter. So we'll have this 3-second triangle that is -3 high, Okay, so that'll be negative 4.5, right? So base times height over 2. 3 times negative 3 is negative 9 divided by 2 is 4.5. Everyone okay with that? Okay. And then I've got this smaller triangle here that's 3 high, 1 wide, so it'll be 1.5. Okay, and that's also a negative number. Then we'll have this really slim triangle right here. Okay, it is 2 high by 1 second wide, so it's just got an area of positive 1. Then we have this rectangle here, okay, that is 1, 2, 3, 4, 5 and a half wide, okay, and it's 2 tall, okay, so 2 times 5 and a half should be 11. My math right on that one? Okay. And then I've got this really slim triangle here that's 2 high by a half a second on the base, so 2 times 1/2 is 1, but it's a triangle, so we have 0.5 as the area of that one. Okay, and then, okay, so the challenge here is to kind of draw all the shapes we have to calculate the areas of. So I've got this long skinny triangle here that is 1.5 on the base by 6 tall, so 1.5 times 6 is 9, divided by 2 is 4.5. So this will be negative 4.5. This triangle here is 4 high by 2 wide, so that's 8 divided by 2 is 4. Okay. Then I've got this rectangle here that's negative 2 high by 1, 2, 3, 4 wide, so that'll be negative 8. Okay, and then this small triangle here is 1 on the base and negative 2 high, so it'll have negative 1, okay, as its area. All right, so that's a pain in the neck. Okay, and on a test, I wouldn't give you a graph that had that many shapes to calculate. It'd be like 2 or 3 tops. Okay, but it gives us good practice at doing it. So now I've got to take all those numbers and I've got to add them up. Okay, do I have to be mindful of the direction? Yes, I do. All right, so I've got negative 4.5 plus negative 1.5 plus 1 plus 11 plus 0.5 plus negative 4.5 plus negative 4 plus negative 8 plus negative 1. Okay. All right, so we got negative, I don't know why I have negative 12 there. That's clearly not right. But okay, whatever. I have a mistake on the key. It should be negative 11. Okay, does everyone follow what we did? All right, so it kind of makes sense that the displacement should be negative. I mean, the graph spends way more time in the negatives than it does in the positive, right? This object is moving backwards a lot more than it is moving forwards. All right, and then we had to find C was average velocity over the whole trip. So we'll take that number we just calculated and we divide it by 20 seconds. So that's not going to be 0.6, it'll be negative 0.55, right? Which rounds to 0.6. Okay, and then for part D, we have average acceleration between 14 and 20 seconds. All right, so let's erase some of what we've done here. Just clogging it up. Between 14 and 20 seconds. So here's time 14 seconds, here's time 20 seconds. So we're going to do that whole A equals VF minus VI over T. So we'll have 0 minus negative 6, and that takes 6 seconds. So we're looking at positive 1 meter per second squared. Okay. And then we want the average speed. So all those distances that we had, we make them all, or all those displacements, sorry, that we had before, we make them all positive, right? Because distance is scalar, right? So all those numbers, okay, that I just had up here, I'm just going to go entry, and I'm going to take away all the negatives. So okay, so there, and then if I divide that by 20 seconds, whoop, right, that'll be my average speed over the whole trip. Okay. And I think because I had this screw up here, all of these other answers have been wrong too. But okay, everyone all right with how we did that? Okay. So a one like that obviously takes quite a while, but it's just good practice. Okay. All right. I want you guys to try a couple more here just to make sure we know or we're confident in what we're doing here. So, okay, try a 5 and 6. Okay. 6 is a little. This is on your on the online thing. You'll probably want to call up number 6 on your phone so you can make it bigger and like read it carefully. For number 5, don't worry about these curves in here. I just couldn't find a graph that looked quite like I wanted it. So just imagine that these make perfect angles instead of curves, okay, at the tops there when you're doing your calculations. All right, both of these are velocity versus time graphs, okay, so keep that in mind. Okay, so for number 5 here, we want to find the total displacement over the whole trip. The big thing was, as I said, make sure that you are treating this like these make triangles. Okay, so here's a, like, or they make perfect angles here. So we're going to have essentially this rectangle here where the object is traveling at a constant velocity of -8 meters per second for 5 seconds. And then we're going to have this part where it's accelerating for 5 seconds, and it continues to accelerate for 5 more seconds on the positive end of this. Okay, like so, and then travels at a constant velocity of +8 meters per second. So are the like positive and negative part of this graph exactly the same? Right? It spends just as much time in the negatives as it does in the positives, doing exactly the same thing. All right. So just by looking at this graph, I should know the total displacement is what? Is 0, because it's totally reflective of the two parts. So I mean, I can do the math of it, okay, and say, all right, for here it traveled at a constant velocity of -8 for 5 seconds, so it went -40 meters, okay, and then here it accelerated from -8 to 0, so that'll be -8 times 5 divided by 2, that's -20. This is +20, this is +40. Well, when I add those up, I get 0 as a displacement. Okay, everybody all right with that? Okay, average acceleration between 5 seconds and 15 seconds. All right, so acceleration, as we said before, is kind of the slope of the line, or the change in velocity divided by the change in time. So we go from we go to +8 from -8. Okay, our initial velocity was -8, our final velocity was +8, and that took 10 seconds. All right, so I've got 16, +16 on the top divided by 10 gives me an acceleration of +1.6 meters per second squared. All right, everyone okay with that? Okay, average speed. To calculate average speed, we need total distance divided by total time. Well, it went 60 plus another 60 is 120 meters, right? Distance doesn't care, it's scalar. And then we divide that by the total time, which is 20 seconds. Okay, 120 over 20 should be 6, right? Meters per second. Okay, no vector on that, no positive or negative, because it's a scalar quantity. All right. How are we doing on number 6? How many people have done 6? Yeah, it's kind of a pain in the neck. That was a lot of work to do on number 6. Okay, give it a little more time on number 6 here. Okay, so if I want to find the average velocity between A and F, okay, then I need to go the displacement during that time divided by the time that takes, right? So between A and F, so F goes to here. So I've got that triangle, I've got that rectangle, this triangle, this triangle, and then this rectangle and this rectangle that I've got to find. Okay, if I find all those areas, that'll be the displacement between A and F. And then if I divide that by 10 seconds, which is the time between A and F, I'll have the average velocity. Okay, that sort of makes sense? Are you guys just not getting the same answer I have? There isn't anything negative on this chart. No. Right, it goes downwards, yes. The acceleration during this part here between E and F would definitely be negative, but the displacement's still positive because the velocity is still positive, right? It's still moving forwards, but it's slowing down. right? So it would be like if someone put a bungee cord across the room, right, and I run into the bungee cord, I'm going to slow down. I'm still moving forward, but I'm slowing down. My displacement's still positive. My velocity is still positive. Yeah? Okay. Okay, are there any other ones that are giving us trouble there? B. Okay, so displacement between A and E. So similar thing here, except now I wouldn't use all the way to F. I would just end there. All right, so if I can find all these areas, so from A to B, we've got a height of 20. 20 times 2 is 40 over 2 is 20. Okay, and then this one here would be 20 times 2, which is 40. And this one would be 20 times 1, 2, 3, 4. So this would be 80. This one here, okay, has a height of 20. It goes from 20 to 40, and it's only 3 long, so it'll only be 60. And then we've got this slim triangle here that's 20 high by 1 wide, and so it's going to be just 10. Okay, so we got 60, 120, 130, 210. Yeah? And so we just got to find all those shapes. That's the tricky part, is just finding the shapes. And calculating area is easy as long as we can find the shapes. Okay, just remember, guys, that when we do calculate those areas, all we're really doing is taking the average velocity during those times and multiplying it by the time. Okay, we're still just using v equals d over t there. Okay, just need a little more time now. Okay, you got an idea of how the rest will work? Okay, if you get done that one, then keep going on to 7. Okay. Okay, so part C in this one asks, what's the acceleration between F and G? All right, well, that's pretty straightforward. I don't even have to calculate anything. What's the acceleration? 0. The velocity is constant during that part. How much would that be out of on a test? 1. Okay, guys, always something to watch for on physics tests. If a question is out of 1 mark, how much calculating do you need to do? None. Okay, it is a recognized type of question. Just you should be able to recognize the answer and write it down. It's either right in front of your face, or it's just something that's like this. Okay, like either the number is right on there and you just have to recognize the number, or it's something like this where there's no calculation and you have to recognize it. Okay, all right. For part E, okay, we want to find the total distance traveled. So we've already done most of that. Okay, we've gotten all the way to E thus far. Okay, so all we have to do is find the rest of the shapes, and we'll have the total distance traveled, because the total distance and the total displacement for this question are going to be the same because it's all positive. Okay, this never ventures into the negatives, so they'll be the same. All right, so I would say I'm going to make a rectangle that goes all the way across to the end, and then that'll finish off my shapes. Okay, so this triangle here is 20 tall by 2 wide. Okay, so 20 times 2 is 40, over 2 is 20. This one here is only 10 tall by 1 wide, so it's only 5. And this one is 1, 2, 3, 4 wide by 20 tall, so it's also 80. Okay, so we had 210 up to E, so 230, 310, 315 meters. Okay, so it's just a matter of, I got to find all these shapes, I got to add them all together, okay, to get my total distance. Right? It's cumbersome, but not like difficult. It's just, we got to remember that's what we got to do. Okay. All right. Okay, 7's a little less intense because there's not as many parts, and the grid lines go all the way across, even though they're blue and distracting. All right, so if you haven't started on 7, give number 7 a try here. Okay, so on number 7 here for part A, if I want to find acceleration, I have to remember that acceleration is final velocity minus initial velocity over time. That formula is on my formula sheet. Okay, so between 7 and 9 seconds. So at time 9 seconds, I'm right here. At time 7 seconds, I'm right here. How much acceleration went on there? Whoops. Sorry, 7 and 9 seconds, sorry. I'm looking at, yeah, okay, sorry, 7 to 9 seconds, right here and right here, sorry. I was gonna say, but this is really easy, it's 0, but it's not. Okay, so here's what we have. We're going from 3 meters per second to 0 meters per second. So VF is 0, VI is 3, and that takes 2 seconds, right? Between 7 and 9 seconds, right? We could also write this formula like this. We could say VF minus VI over TF minus TI. And if we wanted to, that's really what we're doing. I'd go 7 minus, right, 9 minus 7, and I'd have 2 on the bottom, right? Either way will work. Okay, so when I do that, I'm going to get negative 1.5 meters per second squared for my acceleration. All right, questions on that? Okay, for part B, we want to find the total displacement now between 7 and 9 seconds. So that means finding the areas of all these shapes. So our first triangle here is 1 high by 1 wide, so it has an area of 0.5. Okay, this rectangle here runs from 1 second to 7 seconds and is 1 high, so it's got an area of 7 meters. This triangle here is 2 high by 2 wide. Okay, so it's going to have an area of 4. No, sorry, it's going to have an area of 2. Sorry, 2 times 2. Yeah, it's going to have an area of 2. Okay, this rectangle here is 3 seconds on the base, and it is 2 meters per second on there, so that one will be 6. Yep. Is only 6 long, isn't it? Yep. You're right. It's only 6 long. Okay. Yeah, because I forgot about this 1 second I took off here. All right, so we've got 12, 14 and a half. Okay, 14 and a half meters positive for our displacement. All right, so we're just finding the areas of shapes, base times height or base times height over 2. Okay, average speed over the whole trip. If I want to calculate average speed, I need the total distance divided by the total time. I've only got up to 7 seconds, but it's only one more shape, okay, for me to find, and that's this big triangle here. That's 3 high by 2 wide, so 3 times 2 divided by 2 is 3. Okay, so now my total distance is 17.5 meters. Okay, you guys follow what I did there? Right, I just took the 14.5 from before and added 3 on. Right, so I've got a total distance of 17.5 meters. That took 9 seconds, okay, which should give me 1.94 meters per second. Okay. And then lastly, what's the acceleration between 2 and 4 seconds? All right, so we're back to this formula, A equals VF minus VI over T. Okay, we know that's between 2 and 4 seconds, so the time is 2. Okay, the final velocity is 3. The initial velocity is 2. Okay, so we have 3 minus 2. Okay, sorry, 3 minus 1, not 3 minus. Okay, 3 minus 2. 3 minus 1 is 2. Sorry, divided by 2 is 1 meter per second squared. All right. Everybody all right with that? Right? They're all going to work something like that. That question there was an exam question a few years ago. Not all of it, like it didn't have all those parts, okay? But it was that graph. So don't expect something like super complex for a graph. That graph was just a couple of sections. I think on that test, the first question I asked was, what's the acceleration between 4 and 6 seconds? 0. Okay, it was out of 1 mark. Okay, the other part of I think the other thing I asked was, what's the displacement between 0 and 4 seconds? Okay, so people had to calculate this triangle, this rectangle, and that triangle. Okay, and then I asked something like, what was the average speed or something like that between 0 and 5 seconds or something. Okay, I made them do like 3 different things on there, and that was it. Okay, so I'm not going to give you a really complex graph to read. Okay, I'm not going to make it so that you have to do 10 calculations for 3 marks. Okay, that's not fair on a test. Okay, but that's the kind of stuff I'm going to ask. All right. Okay, now number 8, this one's tricky because we kind of only briefly talked about this on the one day. If I want to calculate instantaneous velocity, what did I draw on those curves? I drew straight lines that were tangent. I'm never going to ask you to do that because, like I say, it's impossible for me to mark that, okay, on an exam or something like that. I just can't mark that. So we won't be doing anything like that. Okay. But if I was to do that, okay, like for this, the instantaneous velocity at time 2 seconds, okay, I would have to have a ruler, obviously. You guys would have to have a ruler. And I would draw a line that looks something like that, and then I would try and calculate its slope as best I could. Okay, and for 12 seconds, okay, it would probably look something like this. And make it as long as possible. Okay, something like that. For 17 seconds, probably something like that. And at 20 seconds, something like that. Okay. And then I would calculate their slopes. Again, I'm never going to ask you to do that because it's just too much of a pain to mark it. Okay, because everybody's line is going to be a little bit different. Okay. All right, try that one. Now, what kind of graph is this? Position versus time. Okay, yeah, I know everyone likes position versus time because they're easier. But okay, you have to watch for that on a test. You wouldn't believe, guys, how often people screw up a question because they did all the right work on the wrong graph. Okay. This is seconds, and this is meters. I know it didn't scan very well. So this would be 250. This is 500. This is 750, and this is in meters. Okay, and then this is 100, 200, 300, 400, 500, and that's in seconds. Okay. So again, if I want to calculate average velocity, okay, average velocity, if it's a graph like this and not just one single line, okay, is going to be the total displacement divided by the total time. So between 300 and 500 seconds, right, here's my initial position, here's my final position, so it changes by negative 750, and it does that over 200 seconds. Okay, so if I go 750 divided by 200, I should get negative 3.75 meters per second. Okay, so it's just total displacement over total time. Yeah? So we often use the same formulas on graphs that we would use on a problem, right? Like I could have easily given you guys this question as a problem without a graph, as long as I had told you in part one of the trip, the object went 750 meters in 200 seconds, and then it stayed still for the next 100 seconds. Like I could have described all that, and you would have done this question exactly the same way, right? Just without the graph. It's quicker to do it with the graph. Okay, now the next thing in your workbook, guys, is a big position versus time graph. And we're going to kind of just have a look at that right now, but we're not going to go too far into it. Okay, so it's got this big position versus time graph, and then there's some questions after that about the position versus time graph. So you'll need to have this open on your phone because I can't show both, okay, on here. All right, but the first two questions are super easy. That's all I want you to do. When you're done those first two questions on this graph, then you're done for today.